So there are three types of systems of two linear equations. So think about the graphs of two lines in a plane. Okay, there are three cases that can happen. So the first case that we've seen a lot of is where the lines intersect in a single point. So we have, two lines and they intersect in a single point. Okay, so here we've got two lines where their slopes are both positive. We could have one that's has a positive slope and one that has a negative slope. Or we could have two lines that both have negative slopes. Okay, so in this case, when we've got two lines with different slopes, those two lines have to intersect somewhere. Okay, so given two equations, if we're looking at there's two linear equations and their slopes are different, we know that they have to intersect. Okay, this will help when graphing, because sometimes if the slopes are very close to each other in value, when we look at the graphs on a calculator, they may look like they're actually parallel when they're not. Okay, so if the slope coefficients are different, we know that the two lines do have to intersect someplace. And so a solution to the system then, since we're looking for a point that both graphs share, would be that point of intersection. So it's just going to be a single xy at the intersection point. But two lines may also be parallel. So if we've got two lines that are parallel, these two lines have the same slope. Okay, the steepness and direction of both lines is the same. But if we were to think about eventually where they would cross some vertical axis, they would cross in two different places. So if we're thinking about this as a y-axis, they would have two different y-intercepts. Although they have the same slope, they would have different y-intercepts. And so again, if we're looking for the intersection point, a point that both lines share, these lines are parallel and will never intersect. So this type of system that contains parallel lines would have no solution. Or sometimes in the homework they'll say that the solution set is the empty set. Okay. Well, the third case that can happen is that two lines can coincide, which means that when we go to plot them, they're actually the same exact line. We get two lines that are right on top of each other. So in this case, again, the steepness and the direction of both lines is the same, so they have the same slope. And again, if we think about eventually where they would cross through some vertical axis, let's call that a y-axis, they would cross that y-axis at the same point. So not only do they have the same slope, they also have the same y-intercepts. So again, if we're trying to figure out which points these two lines share, they share all of the points on this line. So we need to be careful and not think that just any ordered pair works. For example, here's a point, and this is not a solution to the system. Because this point doesn't fall on either line, so it's not a point that they share. However, if we take a point that's on the coinciding lines, like this one, this point is a solution to the system because it falls on the graph of both equations, and so it must be a solution to both equations in the system. So in this case, the solution to the system will be all ordered pairs, so all xy on the coinciding lines. Okay, so that part's important. It's not just all xy, but all xy on those coinciding lines. Okay. All right, so in example 7, we are asked to graph and then to solve the system of two equations, 2x plus 3y equals 6, and 4x plus 6y equals 12. All right, so neither of these equations is solved for y, so I'm not going to plot, y-intercept and using a slope, but we can try to find just 2 points that satisfy each of these equations. And so 2 points that are nice to find are the intercepts. So we're going to first find the y-intercept by letting x equal 0, and then find the x-intercept by letting y equal 0. So if we plug in x equal to 0, we get 2 times 0, which is 0. So we're going to get 3y equals 6. So 3 times a number has to give us 6. That number must be 2. So on the y-axis, we have a point at 2. Now, if we plug in, so again, if we think about putting some parentheses around these variables, so if we substitute 0 in for y, we get 3 times 0, which is 0. So we get 2x has to equal 6. So 2 times something has to be 6. So that something is 3. So on the x-axis, we have a point at 3. So again, to get from one point to the other, we went down 2 and to the right 3. And we have a constant rate of change for linear functions. So we can keep using that same slope over and over to get some more points to graph our line. Okay, so now we've got a bunch of points. And so now we're just going to connect those points with a straight line. Well, we kind of missed the points there. Let's try that again. So there's our graph of equation 1. So now let's look at our second equation. So our second equation, we have 4x plus 6y equals 12. And again, we're just going to try to find 2 points that make that equation true. Because we know we have a linear function. We have just x terms, y terms, and constants. So again, if we plug in x equal to 0, we're going to get 4 times 0 is 0. So we get 6y equals 12, so y must be 2. And if we plug in y equals 0, we're going to get 4x equals 12, so x must be 3. Okay, so we can see that we have the same 2 points. And so when we go to plot our second line, it's going to be right on top of our first line. Okay, so in this case, we have coinciding lines. So the solution to the system will be all the ordered pairs on the line 2x plus 3y equals 6. Or you could also say 4x plus 6y equals 12, since they're the same line. So again, keep in mind that a point like this is not a solution. Okay, so not all x, y in the plane work, but any point, so all of these are solutions. So any points on the coinciding lines are solutions, but we've got a whole bunch of points out here, so like all of these, and none of those are solutions to the system. So again, it's not all x, y that work, but just the ordered pairs on the coinciding lines. So if we take a look at this other example, so example 8, we're also asked to graph and then to solve the system using the graphing method. So again, we should recognize that we have 2 linear equations. We have just x terms, y terms, and constants in both cases. So to graph a line, we just need 2 points. So again, we're going to try to find the intercepts. So let's start with our x plus 2y equals 12. So we plug in x equals 0, we get 2y equals 12, so y must be 6. And if we plug in y equals 0, we get x equals 12. Okay, so x equals 12 is a little bit off our axis, but we'll put a point there. And then on the y-axis, we have a point at 6. Okay. And if we compute our slope here, the ratio of change in output to change in input. So output goes from 6 to 0, so it drops 6. Input went from 0 to 12, so it went up 12. We get negative 1 over 2. So down 1 and to the right 2. So down 1 and right 2. Gives us a few more points in here to connect. Let's see if we can hit the dots the first time this time. or maybe not. Call that close enough. Okay, so there is our graph for equation 1. And now our second equation, again, also has just x terms, y terms, and constants. So its graph must be a line. So we're going to try to find just 2 points, again, our intercepts. So if we plug in x equals 0, we get 6 times y, 6y equals 6, so y must be 1. And if we plug in y equals 0, we get 3x equals 6, so x must be 2. Alright, so on our y-axis we have a point at 1, and on our x-axis at 2. And so slope, again, if we look at ratio of change in output to change in input, output went from 1 to 0, dropped 1. Input went from 0 to 2, it went up 2. We can see that we have the same slope, but we have different y-intercepts. So in this case, we're going to have parallel lines. If we actually connect our points on our other graph, it'll be easier to do with a real pen versus virtual here, but we'll try to connect our dots. And we're just going to call that close enough. So in this case, we have parallel lines. The same slope, but different y-intercepts. And so these two lines will never cross. So this system has no solution. So there's no solution. Or again, in the homework, sometimes it'll say the solution set is the empty set.